So in this talk, I would like to share with you some lessons that we learned from working on CoTracker and CoTracker3. CoTracker2 was never a paper, just a model update. That's why we jumped to CoTracker3 right away. At the beginning, I was working on dynamic reconstruction in 3D, and then realized that motion estimation is actually an important part of this problem, and that if we solve motion estimation, we can improve our reconstruction as well. That's why we decided to work on pixel-level motion estimation, and on CoTracker specifically. At the time, there was two different approaches to solve the problem. The first one is single-point tracking, is when you do long-term tracking of individual points. Examples of such tracking are PIPS and TopNet, very good single-point trackers. But then there is also optical flow. It's when you estimate dense correspondences between a pair of frames. And RAP is still a go-to solution in this approach. Single-point tracking has its own problems. For example, if we try to track points sampled on dense grid in this video from the first frame, we can see that there is no global consistency between these points so that they drift relatively to each other. Then optical flow doesn't really have this problem, so that points are globally consistent, but it has another one, the occlusion problem, that background just gets accumulated on the front of the car. In the CoTracker paper, we wanted to be somewhere in the middle, so that we can leverage the advantages of single-point tracking and take some benefits of optical flow and do long-term dense point tracking. The challenges we wanted to tackle here are occlusions, so that optical flow and other trackers fail with occlusions. Then we also wanted to do long-term tracking and account for changes in appearance from the initial frame. And finally, dense tracking is just an engineering challenge. The architecture is the main contribution of the paper, and specifically tracking points together. This is something that allowed us to improve occlusions, tracking through occlusions.
Just a clarification, what's the definition of occlusion?
An occluded point is a point that is not visible in the current frame. And the reason why we wanted to do joint tracking is that if we had multiple points sampled on the same object and some of them were occluded, we could still use visible points to track the occluded points. This joint tracking would actually help to track through occlusions. Then we also had tried to improve long-term tracking with the architecture and the way to train it. We proposed unrolled training. It's something that I will explain a little bit later. Finally, the engineering challenge, dense tracking. We proposed to use proxy tokens to have a more efficient attention. I will also describe it later. What does tracking with CoTracker look like? As input, we have a bunch of frames, video frames, and the points that we want to track. So these are our starting locations. Then we process this video in chunks, so that we start with the first 4 frames in this case. That's our first sliding window. And then we predict tracks into the future. And then we also leverage connections, correlations between different points, and apply joint tracking here. In order to propagate predictions to the future windows, we take the predictions from the current window and copy them into the next window so that the model doesn't start from scratch. Then again, we apply joint tracking, and we do so until the end of the video. At the end, we have predictions for all the frames of the video. And if we are in the training mode right now, that's something that we call unrolled training. It's when we estimate predictions for the whole window, for the whole video, and then backpropagate through all the sliding windows. It's something that they don't do in PIPs, for example, because there they only train one sliding window at a time. While here, the model really learns to propagate predictions into the future sliding windows. That's what we call unrolled training. The model is trained entirely on a synthetic Kubric dataset that consists of 24 frame sequences with physics simulation, shadows, and occlusions. And it's still able to generalize to real data. Okay, now we've trained this model, and it actually solved the global consistency problem. And it can better handle occlusions, what you can see here, so that points don't get accumulated on the front of the car anymore, background points. We can also track points densely in a video, and even the helmet of the biker here, when it goes out of the camera frame, we can still track it. So we had this nice model, and then as soon as we were planning to release it on arXiv and publish the model on the paper on arXiv, this paper came out. That's a really good single point tracker from DeepMind called TAPIR. The problem with this paper was that it was actually initially better than CoTracker. That's a problem for us, right? Because the whole claim of the paper was that joint tracking is better than single point tracking. And here we have this paper. So yeah, CoTracker was somewhere here at the beginning. Then we studied the paper really carefully and noticed that they had a higher feature resolution for their tracking. We decided to try to match their feature resolution and retrain CoTracker with the same feature resolution. And yeah, as you can guess, we ended up somewhere here. Joint tracking was actually better than single point tracking. I think the lesson here is that it's still important to pay attention to hyperparameters, because even if your idea is good, you still need to make sure that everything else is implemented correctly, that all the details are implemented correctly to make it work really well. Now we know that we have this single point tracker. We also know that object tracking is useful, image video segmentation is useful, but how can we apply single point tracking? It was quite obvious for us that visual effects is one potential application, because visual effects artists, just literally track points in videos, and that's a part of their job. So this was quite obvious. But then there was a bunch of unexpected applications as well, such as robotics, for example. At this moment, I believe there is at least 30 papers that use CoTracker for robotics, and most of them do it for imitation learning. It's something that I'm showing in this slide as well. This paper is called any point trajectory modeling for policy learning. And so that's how they use CoTracker in the paper. They have a data set of videos, and they estimate motion for every single video in this data set using CoTracker. Now they have videos with the corresponding point tracks. Then they train a track predictor that takes the action, like folding clothes, as a text token, as a text input, and takes the beginning of each video with the corresponding estimated tracks. And then it kind of tries to predict what's going to happen next so that this action is accomplished. Like, so that this t-shirt, for example, is folded, or like some other action is accomplished. And it shows what the robot needs to do to accomplish this action. This approach is much more data efficient than just training a robot from scratch using teleoperation. Another use case in robotics is temporally consistent object tracking. So point tracking just improves temporal consistency. And then one more surprising application is in bio and medical domains. So that here on the right, we have some proteins being tracked inside human cells. And I'm not really sure what this is for, but apparently it works quite well. And what's surprising here is that the model can still generalize to this kind of data, even though it's trained just on a synthetic data set. On the left, we can see results of tracking using EchoTracker, which is tracking heart muscles in an echo scan. Then some people also track points on animals for research purposes. And one, I think, super interesting application is in video generation, specifically controlled video generation. Because a huge problem here is that it's not always possible to describe precisely what you want to generate. And you really need to generate like hundreds or thousands of videos before you get what you want. Motion estimation adds this fine-grained control to video generation so that you can control like maybe even an eye of an animal, or the camera viewpoint, or the head movement, or things like that. Here is an example of controlling the eye direction of an animal. Then we can also control the camera viewpoint with this kind of motion training. Point tracking, we had one expected application, which is visual effects, and a bunch of unexpected applications, such as robotics, biomedical, and video generation. I think here the lesson is that it's really important to create a nice demo and make your model really easily usable so that people can just try it out and applied in their tasks. It's something that allows to make your model widely usable. And some of the things that we have done right, I think in CoTracker and CoTracker3, are that we had a really nice Hugging Face Spaces and Google Colab demo. We tried to implement an easy-to-use model API and one-liner with TorchHub, so that it's like super easy to just try CoTracker. Then we've also collaborated with AK for the release because he really likes when people have Hugging Face demos. And then we just saw how people used the model and learned from that and iterated, tried to improve and incorporate their feedback. I think it's important to discuss the scientific method because in deep learning research right now, a lot of people just try random things and just like try to see what works, and they don't really use the scientific method here. So what is the scientific method? You start with the prevailing theory, like an existing theory that already solves your problem. You try to identify its limitations, and then you formulate new hypotheses to address these limitations. Then you first critically evaluate your hypothesis and then test the best ones by experiment. And finally, you just adopt the best one as the new prevailing theory. And you iterate because it's never finished. You will always have a better theory. In CoTracker3, we've actually run 200 different experiments when working on the model. And it was impossible to keep track of all these experiments, all the results in memory. So what we've done is we had such a table where we would write down the experiment name, the hypothesis we were testing, the results of the experiment, and the conclusion. And I think it's important to such tracking for scientific research. So that's a template of the table that we had in CoTracker3. Okay, let's try to apply the scientific method on CoTracker. We will start with the prevailing theory, CoTracker, our current solution. Then we will try to identify the limitations of CoTracker. So one of them is that it still cannot really deal with super long occlusions, like 2 lengths of the sliding window or more. Another one is that the architecture is still quite cumbersome. So there is too many components. We want to get rid of them, of some of them. Then there is still a gap between synthetic and real data that we would like to address because the model is trained entirely on a synthetic data set. Let's look at long occlusions. That's an example that's a failure case where CoTracker just fails to track the occlusions and tracks go completely off, as you can see here. The thing that we would like to try is to remove the sliding window processing and process the entire video at once. It's something that we call an offline model because it has access to all the frames from the beginning of processing. If we apply such tracking to this video, it solves the occlusion problem because the model just has access to the very last frames of the video, and it kind of knows the future. So it knows what's going to happen so that it can just interpolate between these frames. A disadvantage of such architecture is that we cannot do online tracking anymore. So that's why we have 2 different model flavors, an offline model and an online model in CoTracker3. Okay, then for the architecture, we would like to redesign it from scratch and remove the global matching stage that they use in TAPIR and some other trackers, and also add for the correlations that I will describe later. So that's what the architecture looks like. We start with the input video as well as the query points. These are the points that we would like to track in the video. And then we start by copying our query points across all the video frames. We also have visibility and confidence outputs in the model. Visibility is just a visibility flag that indicates whether the point is visible in the current frame or not. So we initialize confidence and visibility with just zeros at the beginning. Then we pass all the frames through a feature CNN and predict convolutional features. And then we have our query points that we copied across all the frames. These points at the beginning are all the same in all the frames, so that the vertical relations that we decided to add here work in the following manner. we compute the correlations between the query, the neighborhoods of the query points, and the neighborhoods of all the other points in the other frames. So for this frame specifically, for the middle frame, we compute the correlations between the same neighborhood, because it's the same point in this case. And then we do that for all the frames in the video and pass these correlations to the transformer. We also pass our current track confidence and visibility updates to the same transformer, which then outputs deltas to these quantities. So it just updates all the predictions. And we do these iterative updates 8 times until we have our final track estimates, final track confidence and visibility estimates. And that's what we output from the model. Then the synthetic data problem. The hypothesis here was that we can take our synthetic trained model and fine-tune it on real data that we pseudo-label by diverse teacher models also trained on synthetic data. The idea was to improve our CoTracker without having manually annotated videos. We started with a very simple idea to take a model that we trained on synthetic data, so on Kubric, pseudo-label real videos with this model only, and filter out bad tracks. So keep only the best predictions and train, fine-tune on them, fine-tune the same model on these pseudo-labels. Then as a sanity check, we decided to just try to train the model on its own predictions without filtering out bad tracks. Just see what would happen. So what happened was actually quite surprising to us. The model just kind of improved itself. So we just trained the model on its own predictions on real data, and we got better metrics on the top fit benchmarks. So what we did next, we just scaled the pipeline. We just added more data, more training updates, other synthetic trained models as teachers, and just fixed some hyperparameters. And then we had our scaling pipeline for synthetic models so that we could improve them on real data. And that's what the results look like. So circles here indicate just different models, and then triangles show how they improve after scaling with our pipeline. So the red chart is showing how CoTracker, the original CoTracker, improves with more data. The y-axis is showing mean accuracy on these top fit benchmarks, and the x-axis is showing the number of training of real videos that we use for training. We see that the scaling pipeline improves not only CoTracker and CoTracker3, but also the LocoTrack paper, LocoTrack model. So this worked, which was quite interesting. Now we have this CoTracker3 model with 3 different improvements. We've solved the long occlusions problem. I mean, we did not solve it completely, but we've just improved and made it better. We simplified the architecture and leveraged real data to improve the model. Okay, and now I'm wondering whether you can guess what this video is. I think you can if you work with deep learning research. So it's actually this video. And what I think is interesting here is that we can disentangle motion and appearance and still understand what's going on by just looking at the motion. Here we have motion tracked by CoTracker. And I think that's an early indication that similar models can do even dynamic reconstruction in the future, which is, I think, a very interesting direction for future research.
This is a really interesting paper. I found it some time ago, like 3 weeks ago, I think, and I was really intrigued, especially by the fact that you used other CoTrackers to train, and that you trained only on synthetic data. So can you tell us a bit about how you generated that synthetic data? That's the first question. I'll get few.
Do you mean how we generated for the first CoTracker or the last CoTracker?
Both. That would be
both. Okay.
Ultimate, I guess.
So for the first one, we just used the scripts from this Kubric dataset. The data we are training on, the synthetic data, is from this Google Kubric dataset. And apparently it does not contain any complex motions or shapes. So it's very simple, but it's still enough to train models so that they can generalize. I think because point tracking is a very low-level vision task, so that you don't need to have all kinds of objects that you need for semantic tasks here. And we just use this Kubric dataset with the provided scripts, with the hyperparameters that I described in one of the GitHub issues that we have in CoTracker. And that's it. We just generate a dataset of 10K videos of 24 frames for the original model, and we train on that. We train on 32 GPUs for 2 days.
What's down there? I'm like, is it like you said 1,000 videos, 24 frames each? But I guess
10,000 videos.
Yeah, but what are those? Those are synthetic scenes with synthetic objects purely? Is there any domain randomization? What are the targets, right?
Let's maybe go back to the dataset slide.
So that's synthetic, okay.
Yes, that's what it looks like. That's what we train on. These are just 24 frame sequences, and that's it. That's for the original tracker.
And the objects that are in here are coming from yet another data set, I guess, some kind of object repository.
Yes, so they have ShapeNet and some other data set, I think. I believe these objects don't come from ShapeNet, but from a similar Google data set. I'm not sure. So yeah, it's better to check it.
I was wondering, you mentioned that the data was then labeled, perhaps the objects or the type of motion was labeled using the synthetic trained models. I was curious, what's an example of one of the synthetic trained models?
So for training, we used our CoTracker3 model. So we had 2 models, the offline and online models. So we just used the same models trained on Kubric to supervise our pseudo-labeled training. We also used TAPIR, the DeepMind model that is also trained on Kubric. And we used the original CoTracker. That's it. Yeah, we had 4 different models.
Thank you for the talk. I have actually 2 questions. So first of all is because I can see in some of the movement, especially about the person jumping over the fence, I can see some of the point clouds are actually moving much faster than the background, which does that mean I can actually separate point clouds by depth? In this case, I can isolate this object. If I can isolate this object, does that mean if I have 2 cameras recording from a different angle, I would be able to reconstruct the 3D object just from the point cloud?
In theory, you can do it. In practice, I think the quality is still not high enough. It's not going to work super well. If you have different viewpoints and you track the same points and these different viewpoints. I think the quality is almost there, but not there yet. Maybe we need to train this model with multiple viewpoints as input so that this can work really well. But that's a really good idea, I think. Yeah, that's a way to make it work.
I'm watching this and kind of viewing this as, hey, a potential new tool in the toolbox. And I just had some sort of usage questions. I can immediately see a whole bunch of possible uses, where this could be part of a solution for something else, like dead reckoning, for example. It seems like this would be a super useful tool, for estimating your own position as you're kind of moving through space and things like that. And I was kind of wondering, pushing that a little further, would this be the right tool to use if you're doing something that required, let's say, object tracking? Like, suppose, for example, you had an automated system that was, say, narrating a basketball game. And so you wanted to track players and basketballs. You don't care about the pixels, you care about objects in the scene. Would this be the right kind of tool for that, or would you look for something more object level?
It's possible to use CoTracker for object tracking. It's something that we've seen. I'm going to go back to this slide with robotics use cases. It's something that we've seen here. So here they actually need to track objects, but they track points on these objects instead. I think it's not as good as if you were training a network to track objects specifically, but in some cases it's quite good. And maybe if you want to have positions, to predict positions of specific points on these objects. That's going to be useful, because if you are only tracking one object, then you don't know like where the key point on this object is located. While here you kind of know that. You know that about multiple key points on the same object.